Unbelievable! This electronics hack is actually working. Recently, we received a hint that is really hard to believe. Georg, an experienced developer, commented on our video about loop antennas, suggesting a ceramic vario capacitance for frequency tuning. To be honest, I was skeptical this could be realized using such a simple component. But this diagram from the datasheet made me curious and I started experimenting. Meantime, I became a fan of the idea because it's working with simple capacitors you can buy everywhere. As you know, I love explaining projects that anyone can replicate at home. Frequency tuning of a loop antenna is a beautiful example illustrating the possibilities of this method. It's sensitive at resonant frequency and it's reducing interference. We featured several DIY loop antennas on Electronics Unmasked, which I recommend you to check out. For low frequencies, relatively large capacities are required, making continuous frequency tuning difficult. Mechanical variable capacitors don't exist in the nanofarad or microfarad range. I will explain why in a minute. You can solve the problem using an array of switched capacitors. Well, the method is working, but you need to fiddle a lot finding out switch positions for precise frequency tuning. And a lot of them are required to cover a wider frequency range. Now comes the unusual idea. We are using an otherwise undesirable side effect to solve the problem. Ceramic capacitors are covering the entire range from nanofarad to single-digit microfarads. That's a remarkably high capacitance in such a small volume. To set this into perspective, let's briefly calculate the size of a 1 microfarad plate capacitor. Assuming an air gap of 1 mm, I can calculate its area applying this equation. Here is the issue. 113 square meters would be far too large for a plate capacitor being mechanically variable. The example is also illustrating that sophisticated technology is needed to achieve such a high capacity with these small components. A high permittivity dielectric is needed, and the distance between the conductive plates must be extremely small to achieve it. I would never have thought of it, but in fact there is a strange side effect. Polarization on molecular level in the dielectric is causing an undesired capacitance drop depending on the applied voltage. The so-called ferroelectric effect occurs in X7R or X5R capacitor types. Here's a ceramic 10 microfarad capacitor from a usual set bought on Amazon, and now I'm trying to measure the mysterious effect myself. The 5 kiloohm resistor avoids interference with the capacitance measurement when connecting my lab power supply to the capacitor. A second 10 microfarad capacitor is separating the DC voltage from the LCR meter. At 0 volts, I'm measuring a capacitance of 3.67 microfarad, which I defined as 100%. Actually, it should be 5 microfarads from two 10 microfarad capacitors in series. But that's okay. The manufacturer specifies a fairly large tolerance range. Now I'm applying 1 volt and, strange enough, getting a slightly higher capacitance. At 2 volts, however, it's dropping by more than 7%. At 3 volts, 4 volts and so on, the series capacitance continues to drop, reaching 32.7% at 10 volts. Next, we need a bit math to calculate the green capacitance from the measurements. Indeed, just as shown in the datasheet, the capacitance drops to 20% of the nominal value. That's incredible, isn't it? While this is a headache for a power supply designer, it's a cool feature for something I'm about to show you. One thing I noticed though, the DC voltage in my experiment is much lower than the one in the datasheet. No surprise actually, it depends on the voltage rating. The one from the datasheet is 35 volts, while my capacitors is 10 volts. Keep that in mind if you want to use this effect. Now let's design the application for resonance frequency tuning of the loops explained in earlier videos. Using 2 capacitors in series is crucial to apply DC voltage without creating a short via the antenna loop. On the lower capacitor, the DC voltage is positive, on the upper it's negative, since the circuit is closed over the loop and the balun. But that doesn't matter, the Z effect is the same regardless of voltage polarity. A choke is blocking interfering signals from the DC line, and the resistor remains 5 kΩ as before. It should be less than 10 kΩ, as it forms an RC circuit with the capacitor, delaying voltage changes and thus slowing down the tuning process. My function generator is producing a sweep signal between 1 and 50 kHz, which I'm coupling to the antenna via a second loop. This way, I can directly see its frequency response on my SDR receiver. Cool! I can control the loop's resonant frequency by applying a DC voltage. This allows me to precisely tune the antenna to the receiving frequency. In case your lab power supply is causing such interference, I recommend using a battery and a potentiometer as a variable voltage source. 2 trimmers are adjusted so that you can vary the voltage between 1 and 10 volts. Now I'm computing examples for frequency ranges we can achieve. Assume a 25 microhenry loop and a 7.14 microfarad capacitor. With the simplest setup, I can continuously tune the resonant frequency from 11.7 to 26.6 kHz. Next, we assume the capacitance, consisting out of several capacitors, to increase the frequency range by switching off parts. In my example, I can tune from 11.7 to 257.6 kHz. With the values chosen, we are ensuring a small overlap in the frequency ranges. Remote tuning is possible via a 2-wire connection or even via the coaxial feed as long as high-quality bias tees are used. The findings about ceramic capacitors are crazy, but really interesting. Again, kudos to Georg, and I'm pleased to share his further recommendation. You should prefer X7R over X5R capacitors because their temperature drift is significantly lower. I know many of our viewers are experienced electronics geeks. But has anyone used this effect before? Let us know in the comments. In coming videos we will realize the new tunable loop antenna and we will test it. So stay tuned and support the channel. See you soon in the upcoming videos.